Okay, let's go ahead and get started. Just a couple administrative comments. Let's see what I was going to say. Oh yeah, so I'm handing out problem set 9 now. This problem set's actually a little shorter. And I haven't decided, do you guys want a problem set 10? Because the way that the scheduling is going to work is this problem set will be due next Wednesday. And then a problem set 10 would be due the following Wednesday. And then the exam would be handed out the Sunday after that. Okay. So I haven't decided. I mean, there's a lot of good stuff that I could put on the last problem set. But also having a problem set and the final exam right in the same week is sort of a lot. So do you guys want a 10th problem? I suppose I shouldn't. It's sort of silly of me to ask. Yeah. How about this? It can be optional, but if it's optional grading, I'm not going to grade it. Okay. if you know what I mean. I mean, how about, yeah, how about this? It could be exam practice. Okay. So I'll hand out, I mean, it's a take-home exam, so let's put it this way. I have a bunch of cool problems. And, you know, the last week is going to be on the Dirac equation and stuff like that. And, you know, you may not, that's the sort of stuff you'll be responsible for on the exam, but you won't have a chance to see it on a problem set first. Okay. So maybe what I'll do is I'll just put together some fun problems and hand it out next week as extra fun problems that you can do not to hand in, but just for your own personal education. Okay, how about that? What's that?
We can ask about.
And you can always ask me about those questions. Yeah, of course. The other comment I want to ask, what did you guys think of the problem set that's due today? This is the problem set that every year I teach this class, I have to rewrite it because every year I think I end up confusing a lot. I mean, it's good stuff on this problem set, and the mathematics is actually really not very difficult, hopefully you found, compared to some of your other problem sets. But some people find it a little confusing. I mean, was it all reasonably clear, this problem set? Not really. Reasonably.
The calculations that were asked were usually pretty straightforward.
Yeah.
Then the interpretation of those calculations, sometimes I was lost.
I see. Okay. Yeah. I mean, the point of this problem set was really to introduce you to the way that we use the theory of symmetries to understand particle physics. And yeah, so the calculations were all very easy, but the interpretation, okay. Don't worry too much about the words are just words, okay. If you understand the calculations, then I'm happy. If you have specific questions about the interpretation, I'm happy to answer them. But yeah, so if there are specific questions about the interpretation of the problems, you can always come and ask me. And it's really the case that this is the third time I've taught this course, and every year I try and give a problem set where people work through this, and I have to rewrite, and every year people get sort of confused, and so I have to rewrite it and make it longer and longer and longer. So one of the reasons why the problem was so long is that every year I add more and more explanatory material to the problem set, which might make it more confusing rather than less. I'm not quite sure. Okay. But you should always feel free to give me feedback on the problem sets or ask for interpretations if it's not clear. This next problem set, the last problem set, is actually significantly shorter, I think, and probably at least a little easier than the other problem sets. I hope. I can never quite tell. Okay, but let's go ahead and get started. So today I want to continue with our discussion of time-dependent Hamiltonians in quantum mechanics. So the setup that we are considering is a quantum system with a Hamiltonian that has some explicit time dependence, say a time-varying potential, and we will split the Hamiltonian into two pieces, a time-independent piece H0 and a time-dependent piece V. And in describing the time evolution of the system, it's convenient to expand in a basis of states, which are eigenstates of H0, the time-independent part of the Hamiltonian. And then this time-dependent piece, v of t, will lead to transitions between states. So in order to make this a bit more precise, you could imagine considering a generic state of the system, let's call it alpha, at time t, and expanding it in terms of this basis of states with coefficients that I have called Cn. So Cn is the probability, thank you, that the system will be in the state n at time t. And I've extracted here explicitly a factor of the time evolution operator. So in particular, the phase associated with h naught. And in doing so, it is I'm essentially using what is known as the interaction picture. So the interaction picture is sort of halfway between the Heisenberg picture and the Schrödinger picture. So remember that in the Heisenberg picture, observables change in time and states do not, whereas in the Schrödinger picture, states change in time and observables do not. So in the interaction picture, we imagine that observables, that is to say operators, evolve in time as determined by the Hamiltonian h naught, the time-independent piece of the Hamiltonian. Sorry, that's h naught t. Whereas states evolve in time according to the potential v. So that, for example, if you wrote down the differential equation that determines the time evolution of states in the interaction picture, you find that it's basically the Schrödinger equation, but just with the potential v in the interaction picture instead of the full Hamiltonian. So in the interaction picture, states evolve according to v of t, and observables evolve, that is to say operators evolve according to the operator h naught. Okay. And of course, we could always take our Hamiltonian and split it into two parts in whatever way we like and say that, well, observables evolve according to one part and states evolve according to some different part. And it's simply a convenient bookkeeping device to use this interaction picture where if we wanted to sort of treat h naught as some original Hamiltonian and v as some perturbation on top of that Hamiltonian, to use this so-called interaction picture. Okay. So is this clear? Does everyone remember this from last time? Hopefully, a couple nods at least. Just one point of clarification, of course, that vi at time t is e to the I h naught t over h bar times v of t times e to the minus I h naught t over h bar, according to this formula up here. Yes, there's a question. Was that your question?
No.
Okay.
For the Schrödinger alpha state here, this state is time dependent.
This state is time
And
dependent.
you're removing the time dependence.
So the point is that normally you have either states or operators time dependent. Now we're taking them both to be time dependent. Okay. And we're separating out the source of the time dependence in two different ways. We're saying that states evolve according to v and operators evolve according to h. Now, that means that v, which is this interaction term in the Hamiltonian, that time-dependent piece, that itself is an operator. And so it has some explicit time dependence because, well, we're studying time-dependent Hamiltonians. But it also has some time evolution just because it's an operator that will evolve in the interaction picture according to this equation. Okay. Good. Any other questions? So in terms of this, if we then just compare this equation, so that, of course, is the Schrodinger picture state. So in interaction picture, we just remove that phase, and the coefficients Cn that tell you the probability that the system is in a given state at a given time are just the coefficients in the expansion of this interaction picture state in terms of the Hilbert space n associated with H naught. And this allowed us to easily derive a differential equation that is obeyed by these Cn's simply by taking the derivative of this equation. So I h bar Cn dot is the overlap of n with the time derivative of alpha I, which is determined by this equation up here. So that's the sum over m of, well, let's write this as vi alpha I, which we can then use this equation to write as the overlap of n with vi times the sum over m Cm of t m. Or we can rewrite that equation a little bit by pulling out the sum over m as the sum over m Cm times the overlap times the matrix element of the interaction picture potential, which, using this equation up here, becomes the equation I h bar Cn dot is the sum over m Cm times e to the I, a phase factor that comes just from the evolution, that comes from these Hamiltonians that appear up here. So e to the I times the energy difference times t divided by h bar times Vnm, where Vnm is the matrix element of the original Schrodinger picture perturbation V of t between the states n and m. Okay. And this is the formula that we ended with last class. And it's a first-order differential equation that you will have to solve in order to determine the probability that the state will transition from the system will transition from one state to another due to this time-independent interaction. So this is basically a first-order vector differential equation. So schematically, you could think about this C as a vector with some number of components that is equal to the dimension of your Hilbert space. And then this equation says that I h bar times the time derivative of that vector is some matrix acting on that vector. Oops, with no time derivative. Where that matrix is just the matrix whose components are given by the right-hand side of that equation up there. Now, of course, there is a generic solution to a matrix differential equation of this sort. So you can actually solve it generically in terms of, can anyone tell me the answer? Can anyone tell me what technique you would use to write down the generic solution to this equation? How about a hint? Let's say, what if C were a matrix instead of a vector, and you were trying to solve a differential equation of that sort? I'll give you a hint. We've already seen it in this class. We spent a whole lecture on it. What if I, instead of writing C, I called it U, and instead of writing M, I called it H? Does that differential equation look a little more familiar?
Is it
Yes, you would have to use a time-ordered exponential to solve this. And indeed, that is what we're going to do a little bit later in class. I'll use time-ordered exponentials to write down a generic solution to this equation. But before I do so, let me just consider a particular example. And this is actually one of the most famous examples in quantum mechanics. It's an example that leads to all sorts of interesting effects that are both interesting for physics as well as interesting for lots of other reasons. Okay. So let's consider a two-level system subject to a periodic potential V of t. Okay. So H naught I'll just take to be the Hamiltonian of some two-level system. So I'll call those states state 1 and state 2. So this is what your Hamiltonian operator will be, your unperturbed Hamiltonian operator. And V of t is going to be something which is periodic in time and will cause transitions between these two states, the first state and the second state. So I'll just take it to be some generic off-diagonal operator in the 2x2 matrix language. So I'll take it to be something like gamma e to the I omega t times the operator that takes you from state 1 to state 2 plus the Hermitian conjugate of this operator, where gamma and omega are just going to be some real numbers. Although I suppose in principle I could take gamma to be a complex number, but just to keep things simple, I'll keep gamma and omega real. Then our differential equation, so then let's compute this V and M here. So V12 is gamma e to the I omega t, and that's the, of course, V21 is the complex conjugate of this. So if you wanted to rewrite that differential equation that I wrote down in the box above in matrix language, it's the statement that IH bar times the time derivative of the column vector with components C1 and C2 is equal to that matrix, which is going to be the matrix with off-diagonal elements gamma e to the I omega t times e to the I omega 1 2t 0, and with the complex conjugate of that guy, e to the I minus I omega t minus I omega 1 2 t, acting on C1 C2, where omega 1 2 is just the energy difference between the two states, where I've introduced a factor of h bar in order to give that guy units of 1 over time. Okay. So it's a straightforward exercise to go ahead and plug in, just evaluate the boxed equation up above here in this particular case in order to obtain this differential equation. Okay. All I've done is rewrite it. And then it's an equally straightforward exercise to solve this differential equation in order to determine how C1 and C2 evolve in time. And it's a good thing it's a straightforward exercise because it's one you're going to do on your next problem set. Was there a boo? Did I hear someone boo? Okay. That's not called for. Okay. So let me just tell you what the answer looks like, because the answer is actually one of the more important equations in quantum mechanics. So let's just consider the simple case. Let's consider the case where we start with all of our states at time t equals 0 in the lowest energy state, state 1, so that C1 is equal to 1 and C2 at time t equals 0 is equal to 0, so that initially only state 1 is populated. Then if you go ahead and solve this differential equation as a function of time, what you'll see is that, in fact, the probability that the system is going to be in state 1 and state 2 will oscillate in time sinusoidally. And so that C2 squared as a function of time, the probability that the system is in state 2 is some normalization factor which depends on the amplitude gamma of the perturbation, as well as on the frequency omega of the perturbation and the frequency omega 1, 2, that is the energy separation, that is determined by the energy separation between the two states of the system, times something which evolves sinusoidally in time, where omega is something that you will compute. Okay. It's actually also in your textbook, but you'll compute it anyway. And, of course, the absolute value of C1 squared, the probability of being in state 1, is just 1 minus this guy. So what we see is that this oscillates with some frequency omega that is determined by the various parameters in the system, and with an amplitude that is maximized when omega is equal to omega 1, 2, which is the energy difference between the states in units of h bar. So if you think about it for a minute, this should in fact remind you considerably of a system that you have already seen. And that system is the driven harmonic oscillator. So if you have a harmonic oscillator which has some natural frequency omega, and you drive it with by imposing some external force with some frequency omega prime, then typically the system will have some very complicated behavior. But the amplitude of the oscillations in the system will be maximized when the driving frequency matches the natural frequency or the resonant frequency of the oscillator. And essentially what we're seeing here is the quantum mechanical version of the system. So this condition is a resonance condition and when you drive the system with a frequency that precisely matches the energy splitting between these two levels, it's possible for the system to be completely in state 2. So in particular, if you look at this formula that I've written up above, and if you set omega equals to omega 2, 1, then that amplitude in front of the sine squared omega t is just going to be equal to 1. So what this means is that for a generic driving frequency that doesn't match exactly the energy splitting between these two states, the system will always have some probability to be in state 1. But if you're precisely at the resonant frequency, then it's possible to completely transition from state 1 to state 2. And of course, you'll oscillate between them with a frequency capital omega. So why is the system important? So the system is important for a variety of reasons. So this is essentially how we know everything about nuclear structure. In particular, if you want to delicately probe the quantum mechanical features of some system, say, the energy levels of some quantum mechanical system, such as a nuclei, then essentially what you do is the following. So this is known as nuclear magnetic resonance, or NMR. So what you do is you take a spin 1/2 particle, such as a nucleon, or you could take some more complicated object with higher spin, as long as it's made of some constituents that have charge, and apply a B field, which is constant, in the z direction, subject to a oscillating piece, B of t, which will be something that oscillates with some characteristic frequency omega in the xy plane. So what does this do? Well, first of all, if you just have some spin 1/2 system hanging out, not subject to any potential, then its two energy levels will be degenerate. So, for example, a proton or a nucleon of some sort. And then you apply a constant magnetic field. That will lead to an energy splitting between the two states, which in the case of a magnetic field for an electron is the spin precession frequency. Which you've presumably seen before. This is the energy splitting between states if you have the Hamiltonian, which is the spin 1/2 spin operator, namely the Pauli matrix, dotted with the B field. So you guys have seen that before? Okay. This is just the statement that if you take a a magnetic field pointing in some direction, and you have a particle with charge and spin, then such as an electron, then that electron will want to be aligned with the magnetic field. And so that means that the two previously degenerate energy levels will be split, because there's one state where the electron is aligned and one state where the electron is anti-aligned with the magnetic field. And so by imposing this constant magnetic field, you're splitting the energy levels. And then you introduce a time-dependent field. And as you vary in omega, you will get peaks in the transition amplitudes at the various energy splittings. So for example, for the simple case of an electron in a magnetic field, you'll get a peak when omega is equal to omega 1,2. But if you have some much more complicated object, such as a big nucleus made out of all sorts of fundamental particles that you don't really understand very well, you put it in a magnetic field, you scan over the possible values of frequency, and you get some complicated picture, which is the transition amplitude as a frequency of omega, and the peaks all correspond to energy level splittings in the nuclei. So this is how we know the energy levels of nuclei. And this is actually also the physics behind MRIs and a lot of different medical physics. Essentially, this is one of the best techniques for probing the internal structure of various different sorts of materials, whether they're nuclei or people. Yeah, and I should say that this has a name. This is known as Rabi's formula. Okay, good. You guys have not seen that before. Okay. So this was a very simple case where we could actually solve exactly for the transition amplitudes as a function of time. But for most time-dependent potentials, we can't solve for these transition amplitudes Cn exactly, and instead we must use some sort of an approximation. So let's consider the following problem. So let's suppose we start in a state I, which is the initial state at time t equals t naught. And then we wish to discover what state we're in at some later time t. So we could work in the interaction picture, if we like. So that this, of course, would be the sum over n of these coefficients Cn of t times the state n. And I'll write Cni here, okay, just to denote the fact that we started in an initial state I at time t equals t naught. And because I of t evolves according to a Schrödinger equation, but it evolves according to a Schrödinger equation associated just with the potential v of t, not with the full Hamiltonian h naught plus v of t, you could write this as a unitary time evolution operator acting on your initial state I at time t naught, where this operator u is the unitary time evolution operator for states in the interaction picture. So it will obey an equation which is exactly the same as the equation that the unitary time evolution operator always obeys. Here, I'll write out my t's explicitly. Except that in the right-hand side, instead of having h plus vi, h naught plus vi, the full Hamiltonian, you have only the interaction part of the Hamiltonian, only this time-dependent piece v of t. Okay. Is this clear? Hopefully this should be more or less clear. It's just a simple consequence of the fact that I'm in an interaction picture and I'm subtracting out the time evolution associated with h naught. Okay. The full time evolution operator u in the Schrödinger picture would be ui conjugated by the operator e to the I h naught t over h bar. So that means that one can solve for this unitary time evolution operator in exactly the same way that we did earlier in this course when we studied the path-ordered exponential. So in particular, the result is the path-ordered exponential, not of the Hamiltonian integrated over time, but just of the interaction picture time-dependent part of the Hamiltonian v of t integrated over time. And I remind you that this path-ordered exponential is defined in exactly the same way as the normal exponential. So it's defined in terms of its expansion of the exponential in terms of a Taylor series. So the first term will just be the integral of v from t naught up to t. The second term is a double integral. So integral dt1 from t naught up to t, and then an integral dt2 of the product of these guys, vi of t1, vi of t2. And the magic of the path-ordered exponential is that you integrate from t2 only from t0 up to t1, rather than from t0 up to t. And this is the effect of ensuring that t1 always occurs before t2 in terms of the operator ordering of this term in the Taylor expansion. And it is precisely that reordering of operators relative to the usual exponential that allows you to solve this differential equation for the unitary time evolution operator. Okay. What is the point of this? So this expansion is known as the Dyson series. And it gives a good approximation when the perturbation v of t is small. In particular, you can just work order by order in this perturbation expansion of this unitary time evolution operator u. So in particular, Cn of t, I guess I called it Cni. Okay, I'll just call it Cn of t, is the overlap of the unitary time evolution operator acting on your initial state with the state n. And then we could expand this order by order in a perturbation expansion simply just by keeping, so this is our expression for ui, the subsequent terms in this Taylor expansion for u order by order in the potential v. So if you imagine that v is very small, then this will be hopefully a very good approximation to the time dependence of the full system. So that, for example, Cn at time 0 is either 1 or 0, depending on whether our n is equal to the initial state or not. Okay, because the first term in this expansion is just 1. Okay, so at leading order, v is you forget about v, and your system doesn't evolve in time, except in the trivial way associated with h naught. The next term in this expansion is the term that you get if you just take this operator here and sandwich it between n on the left and I on the right. So that's minus I over h bar times the integral from t naught up to t dt1 of the matrix element of this operator vi, or if we want to write this in terms of the potential v in the Schrodinger picture rather than in the interaction picture, this is minus I over h bar times the integral from t naught up to t dt1 of e to the I omega n1 t times v n I of t, where again omega ni is the energy difference between the two states in units of h bar, and vni is the matrix element of your perturbation between those two states. And finally, we could work at second order. So see the next coefficient. What is that? Well, that's just the matrix element of this operator between the states n and I. So let's just write that down. It's minus 1 over h bar squared times the integral dt1 dt2 from t naught up to t and t naught up to t1 of this matrix element And it's actually instructive to write this out explicitly by inserting a complete basis of states in between these two v's. So this is minus 1 over h bar squared times the integral dt1 integral dt2 times a sum over all intermediate states, which I will label by m, of the phase e to the I omega nmt vnm at time t1 times the phase e to the I omega m I t times vmi at time t2. Where here this m, as I mentioned, is the sum over intermediate states. And this formula just arises when I insert right here the sum over intermediate states here, and I use my definitions of omega and the matrix elements of V. Okay. And so on and so forth. And if we were really excited, we could go ahead and write out the third and the fourth order terms in this expansion explicitly. But there's a reason why I've taken the time to write out the terms in this expansion explicitly. Because there's really a lovely picture that goes along with this. Okay. In particular, the term CNI can be regarded as describing the situation where the system interacts I times with the potential. So if you want to have a picture in your head of what's going on here, you can imagine the following. Okay, so let's take a look at these terms that are sitting here. So you can imagine that we're studying a system where you have an electron that's scattering off of a nucleus. You could look at this from the electron's point of view, where you have an electron that's passing by a nucleus. And that means that the electron is subject to some time-dependent potential due to the electromagnetic interactions with the nucleus. And then if you ignore those interactions, then you'll just get the term Cn0 that I wrote up at the top. And then at first order in our perturbation expansion, the electron would interact exactly once with the nucleus, and that would give us Cn1. In the second term in our expansion, the electron would interact twice with the nucleus. And in particular, it would interact once going from state I to state M, and then a second time going from state M to state N. So the picture that we would use to describe this is that Cn0, you would imagine that you have some potential V here, which is some nucleus, and the electron would go through without interacting at all. Cn1 would be some picture where you have a potential, and the electron interacts with it once. So you might denote that by a little cross. Cn2 would be a picture where the electron would interact twice, and so on and so forth. And the state N, so the initial and final states here, you could label on this diagram. So at 0th order, N is equal to I. At first order, N and I can be different. At second order, you have some intermediate state M, and so on and so forth. Okay. So we give a name to diagrams of this sort. So what I'm doing here is I'm writing out the unitary time evolution operator that describes the evolution of our system. And instead of writing down a formula for each term, I'm writing down a little picture, and that picture tells us in our head what formula we're supposed to write down. This picture is a convenient way of encapsulating that formula. These pictures have names. They're known as Feynman diagrams. I don't ever remember how many N's are in his name. Feynman diagrams. These are sort of baby Feynman diagrams. They're a little simpler than the full glory Feynman diagrams that you might use in some more refined version of perturbation theory. But essentially, what we've worked out here is everything that you would need to work out in principle if you wanted to develop the theory of Feynman diagrams. Okay. Now, for the purposes of this class, Feynman diagrams are not particularly useful because the formulas that we write down are not so complicated that we can't just write them down. But when you're studying more complicated quantum mechanical systems, where you want to keep track of many, many different types of particles, types of intermediate states, types of interactions, and so forth, diagrams of this sort become more and more useful as far as keeping track of the formulas that you would want to write down. So the slogan that you should keep in mind is that whenever you expand your unitary time evolution operator, order by order in your interaction, the name for the different terms that you keep order by order in your interaction are Feynman diagrams. And the one thing that I should mention is that the expansion in powers of v is also an expansion in powers of 1 over h bar. Okay. Why is that? Well, that's just because u is the exponential of e to the integral v divided by h bar. That's just, it has to be by dimensional analysis. Energy times time has units of h bar. So when we write down expansions of this sort, it can be viewed in two different ways. It can either be viewed as an expansion where the potential is taken to be small, or it can be regarded as a classical expansion. Okay. I.e., it is a semi-classical expansion where each successive term in this perturbation series tells you about more and more subtle quantum effects. Any questions so far? Okay. So the total transition probability is the absolute value squared of one of these guys. And it is this object that we are very often interested in calculating. So very often, we never calculate the phases that appear here. We never actually observe them. You just observe whether the system has undergone some transition or not. Okay. So, for example, in scattering theory, this is the sort of situation that you might be interested in. Okay. So let's consider a very simple example. And this is the example that would be relevant if you want to imagine for a situation like an electron that's scattering off of a nucleus. Okay. You would imagine in some simple approximation that at times less than t equals 0, you have no potential, and then you just switch on a potential at time t. This is the simplest possible approximation you could make for a time-dependent system. Then this first order guy, what is that? Let me just write that down for you again. That's the minus I over h bar times the integral dt1, integrated from t naught up to t, of the matrix element Vni times e to the I omega ni t1, where this matrix element Vni is now independent of time. So I can just go ahead and do that integral. So omega ni is the energy difference divided by h bar. So when you do this integral dt1, you pull down a factor of 1 over omega ni. So canceling the factors of h bar, that gives you an en minus ei in the denominator, times 1 minus e to the I omega ni t minus t naught. Oh, I said, let's just, I guess that's, it starts at 0, right? Because our potential switched on at time t equals 0. Okay. So you're imagining that you start the system in the very far past in the state I, and then you integrate from the very far past up to time t. But for times t less than 0, the potential is just equal to 0. So you do this integral from 0 up to t, so that the transition probability is the absolute value squared of this. So that is the absolute value squared of this matrix element divided by the square of the energy difference between the initial state and the final state, times the absolute value squared of this guy here. And what is that? Well, the absolute value squared of that is just sine squared of that frequency omega ni t divided by 2. So that's just taking the absolute value squared of this guy here. And so you see that somewhat similar to the two-level system that we considered earlier, the transition probability will oscillate in time with a frequency that is associated with the energy difference between the levels. The difference here is that you have this 1 over en minus ei squared in the denominator, which tells you that it is harder to transition to states with different energy. A priori, this might seem a little surprising. You might think that it's easier to go to a state with lower energy and harder to go to a state with higher energy. But that's actually not quite the case. These transition probabilities will fall off very rapidly as the energy splitting between the initial and final states is increased, whether positively or negatively. So we're often interested not in a particular final state, but rather a final state that is in some window. So, for example, if you have a system with lots and lots and lots of energy eigenstates that are very closely spaced, then you might not be able to measure precisely the final energy, but only constrain it to be inside some window. So let's call the number of states in the window between E and E plus dE, where dE is some small number, the density rho of E times dE, then the transition probability, which is the sum over all n of this individual transition probability Cn inside the window, so this is the total transition probability. That's the integral from E1 up to E2 den rho of En of this guy that I computed for you earlier, which I'll just write down again for you. So that's En minus Ei over 2h bar t times Vni squared divided by En minus Ei squared. So this is the total transition probability for our system starting at some state I to transition into some window, some states inside some energy window with energy between E1 and E2. And all I've done here is write down the first order term in that Dyson series expansion and essentially write it out not in terms of an individual energy state, but rather in terms of some density of energy states, some spectrum of energy states with densities rho of En. Now there's something interesting to note about this formula. Which is that at very late times, this sign actually becomes a delta function. So this is just some mathematical fact. So in order to understand it, let's look at the graph of that function, sine squared of tx divided by tx squared. So for a given value of t, it might look something like that. And then as t is increased, it becomes more sharply and sharply peaked around that center there where x is equal to 0. And so, in fact, in the large time limit, this expression for the transition probability simplifies greatly. And because of this delta function, En will approach Ei at late times. So at late times, the system will transition only to states with energies that are very close to Ei. And the sum, the total transition probability, will grow linearly in time. That's just the statement that if you compare this formula here to our formula for the delta function, I had to divide by t to get the delta function. So you could multiply both sides over here by t, and you would get a t over on the right-hand side. So that means that it makes sense not to talk about the transition probability per se, but instead the transition probability per unit time which is d by dt of this total transition probability. Okay, so factoring out that divergence with t at late time, this then, plugging in this formula up here, and using the delta function, so at late times this becomes a delta function that sets En equals to Ei. It's 2 pi over h bar times Vni squared times rho of En with En equals to Ei. And we sometimes abbreviate this with a little omega. We call that the transition probability from omega to n. This is actually one of the another quite famous formula. This is known as Fermi's golden rule. And it's essentially the basic starting point for the theory of scattering. It allows you to estimate the transition rate for a system to first order in the potential. And basically, what it tells us is two important things. So first of all, it tells us that at late times, energy is conserved since En has to be equal to Ei, but that at finite times, energy is not necessarily conserved, so En is not equal to Ei. And this actually is a precise way of making sense of the energy-time uncertainty relation, as you'll see on your next problem set. So the statement that if you only look at finite times rather than late times, En is not equal to Ei, means that essentially if you want to measure energy levels completely precisely with arbitrary precision, you need to perform an experiment that lasts a very, very long time. And alternatively, if you want to perform an experiment that only lasts a very short time, then the energy fluctuations can be very large. Okay. So the energy-time uncertainty relation, delta E, delta T, is greater than or of order h bar, is an uncertainty relation that's on somewhat different footing from the usual Heisenberg uncertainty relation that we've considered previously in this class. When you consider the uncertainty relation delta x, delta p, it's completely clear what you're talking about in quantum mechanics, because x and p are operators, and delta x and delta p are the variances of those operators computed in some state. And so we know it's completely clear what we mean by the Heisenberg uncertainty relation in those contexts. Here, when you're talking about E and T, those are not operators in quantum mechanics. E is an operator, it's the Hamiltonian, but T is not exactly an operator in quantum mechanics. It's a parameter that you use to label the states of your system as the system evolves in time. So the interpretation of the energy-time uncertainty relation is a bit more subtle and a bit different from that of the position-momentum uncertainty relation, for example. And really, the correct way of thinking about the energy-time uncertainty relation is in situations like this, where you're looking at a transition probability as a function of time, and if you want to narrow down the window of energies that you transition into, then you need to perform the experiment for a very, very long time. And if you want to just give an order of magnitude estimate for the relationship between delta E and delta T, then of course, just by dimensional analysis, you would expect some formula like that to be true. The question really is, what is the dimensionless constant that sits out front? And that's something that you are going to explore on the problem set that you just picked up. The other thing that I should mention is that implicitly, I'm assuming that Vni, I won't even bother to write it down, I guess. Implicitly, I'm assuming that Vni is independent of the energy here. If it's dependent on the energy, then we would need to take that into account, and we would need to correct this formula somehow. So for example, you can imagine, I did some integral here using the delta function. you could imagine that V and I might depend on other parameters in addition to the energy, some other quantum numbers in the system, some other conserved parameters. And you would have to include those in your final analysis if you wanted to take that into account. Okay. Let me finally mention one more comment about this. Okay. So Fermi's golden rule followed from the first order perturbative term in the Dyson series. And at next order, we could write down Cn2. Okay, what was that? Let's go ahead and work it out. So here we would need to work out this term here with a constant potential. So let me just go ahead and rewrite it for you. Well, actually, I'll just go ahead and tell you the answer. It's just some straightforward t integrals that we need to do. So what is the answer? There's an I over h bar times the sum over n times vnm, vmi, divided by en minus ei. So that's just doing the time integral times the integral dt1 from 0 up to t of e to the I omega ni t1 minus e to the I omega mn t2. Sorry, that's having done the t2 integral. And then we can then do the t1 integral. I won't bother to write this down explicitly, but just tell you what the answer is at late times. The transition rate, which is the time derivative of this, again, is proportional to the density of states. And so the first order term in the perturbation series is just Vni. And the next order term involves the sum over intermediate states. I'm sorry, that was, yeah, it's actually good. Divided by the energy difference. And the important thing to notice here, I mean, I haven't gone through all of the details. It's a completely elementary exercise in doing those time integrals. They're just integrals of exponentials and computing the square, is that the intermediate state need not conserve energy. So we saw at late times, we had that delta function that told us that En had to be equal to Ei. But at finite times, but when you work at higher order in perturbation theory, what one finds is that the intermediate states, Em, need not have energies equal to Ei or En. So that in terms of this picture here, the initial and final states have equal energies, but the intermediate state can have some energy that is not equal to that of the initial or final state. And this is known as a virtual transition. Why is it called a virtual transition? Well, we've seen that real transitions between initial and final states always conserve energy at the end of the day. So the energy of the initial state is equal to the energy of the final state, at least at late times. But it's possible to see the effects of transitions to intermediate states with different energies. And they're called virtual because you never actually see them. You only ever see the final state rather than the intermediate state. And in fact, this notion of virtual transitions and virtual states is something that appears very frequently when you consider scattering theory, when you consider quantum field theory, and it's really one of the core concepts that's developed when you study quantum field theory. Okay. Let me pause here and see if there are any questions. Yes. Yeah.
If you're interested in angular distribution after scattering, can
Good.
you just do that and then use momentum conservation?
Yeah. So actually, the angular momentum behavior scattering is really interesting. So it's sort of a shame that I'm not doing scattering theory in this class. Maybe I do think I had one lecture. Maybe I'll think about doing scattering theory. But roughly speaking, if you want to understand angular momentum, actually the best way of studying scattering is if you're doing scattering off of a radially symmetric object, so like the scattering of an electron off of a nucleus, then what you want to do is you want to expand in spherical harmonics, and you get a one-dimensional scattering problem for each spherical harmonic. And this is what's known as the method of partial waves. It gives you exactly a way of studying how, for example, energy and momentum can be transmitted. And indeed, I think as you were getting at with your question, angular momentum is conserved. So that means that you won't transition between different angular momentum states in the scattering process. I think, yeah. It's been a while since I taught the method of partial waves, so I would need to remember exactly how that works, but yeah. Yeah. Any other questions? Have you guys seen Fermi's golden rule before? Sometimes you see that. Did you see it in this form? You saw it in some other form. I see a couple people nodding, but maybe people who weren't here. Okay, I don't know. Yeah, good. Any questions? Other questions? So this wraps up just about everything that I wanted to say about time-dependent systems and quantum mechanics. I should mention that I have arranged for you guys to get a lecture while I'm out of town from someone who works on Berry's phase. So adiabatic time evolution in Berry's phase is something that's very important for the consideration of various sorts of condensed matter systems and various sorts of material systems. Basically, it's like a souped-up version of the Aharonov-Bohm effect that we've already seen. And it's really cool, so you'll get a lecture on that. But aside from that, I think that's about all I wanted to say about time dependence in quantum mechanics. And so I have to decide exactly how I'm going to structure it, but I think starting next time I'll talk about relativistic quantum mechanics. And I think I actually am ending early for the first time this semester. So are there any questions? This is the only 7 minutes you're going to get where I'm ending early. It very rarely happens. Yes. Any thoughts about quantum mechanics? No? Okay, I'll see you guys on Friday then.